Okay, welcome to another Orbiter 2010 video, and this video is going to be a direct continuation of the previous video that I did in my Absolute Beginner Guide series. This is a series that I'm putting together that has a special emphasis on people who are brand new to Orbiter. You've downloaded the program, you've got it installed, but you really don't know how to do anything with it. So if you watch these videos, we'll learn how to get into orbit, we learn how to raise and lower our orbit, we learn how to do plane alignments, how to get to the International Space Station, how to land. And in this part of the series, we're learning how to go to the moon. So I'm assuming that you've already watched all of the previous videos in the series. So if you're happening on my channel for the first time in this video, then you're going to want to stop this video, go back to part 1, and watch all the videos in order. Now that I've said that, let's get back into the flight here, where we're eventually going to get to the moon. Now in the last video we took off from Cape Canaveral, and I just discussed a couple of basic concepts, such as making sure that we're going to arrive at Brighton Beach when the sun is up, and then we talked about getting up into orbit while having our relative inclination between our orbit around the Earth and the moon as low as possible. So let's go ahead and continue. Let me unpause the video here, or unpause the simulator. Now we just did reach main engine cutoff, so we're here at 96 kilometers, and we've got our orbit basically established. It's in pretty good shape, but we still have a couple of things to take care of. The first priority when you get into orbit always is to make sure that you're going to stay in orbit, because it doesn't do a lot of good to do other orbital tasks if you only then go around the globe one time and get into the atmosphere and burn up. So we want to first just see when we need to do our orbit circularization burn. That is always the #1 priority when you get into orbit. And I can see here the time to the apoapsis is 1,473 seconds and counting down 1 second at a time. And the apoapsis is here. If I press mod to get rid of the information, you can see I'm here and my apoapsis is here. And again, that is 1,459 seconds away. So the highest priority for me is to make sure that I get to that point and circularize my orbit. But there are other things that I can do in the meantime, because I can't circularize the orbit until I get to this point. At least I can't do it efficiently. So if there are other things that I can tend to before I get to that point, then I want to tend to those things. One of those things that I can tend to is my align plane. I can see over here in align plane MFD that I'm going to reach the descending node in 663 seconds. Now, it's pretty easy to understand that 650 seconds or so is a lot less than 1,400 seconds. In other words, I'm going to get to this point, and I'll still have 800 seconds until I get to that point. So if there's something that I can do at the descending node, I can go ahead and tend to that first. I don't have to. I can skip it and take care of the orbit circularization and then do the align plane. But since I'm going to come up to the descending node well ahead of schedule for getting to the apoapsis, I want to take care of this first. So I'm going to press H to change over to orbit Earth. And now that I'm in space, I can switch over to the better looking green color. And there's really not much else I can do except warp time forward until I get to the descending node. I will say this though, if you want, you can come up to the 2D cockpit view and press the down arrow to get access to these additional switches. And if you want, you can extend the radiator. And this is actually not a bad habit to get into. For the sake of the standard Delta Glider, it actually serves no purpose. The Delta Glider doesn't utilize the radiator. It's just an animation. It's just for looks. However, when you use the Ravenstar or the Vanguard or certain other vessels, it is absolutely required that you extend the radiator once you get out into space, and that's for the sake of cooling. So it's not necessarily a bad idea to go ahead and do that for the Delta Glider as well, just to develop the habit. So now that the radiator is extended, go ahead and press F1, get back inside the cockpit here, and I'm going to come back to this view because I like it better for the sake of the video playback. These larger MFDs just show up a lot better. So now that we've got everything more or less set up, we can just kind of warp time forward until we get to the descending node. But let's do a basic review of what we're going to do when we get to that point. When we get to the descending node, which orientation do we need the vessel to be in? Do we need to be prograde? Do we need to be retrograde, or some other orientation? Hopefully you remember from the videos earlier on when we talked about so much about plane alignment that the correct orientation for the descending node is orbit plus, or normal plus. And just briefly, that's because AN equals AN, that's ascending node equals anti-normal, and anti-normal is normal minus. So descending node is the other one, and that would mean that descending node is normal plus. So before we get to the descending node, we need to be in this orientation. We don't necessarily need to do that now because we're still quite a ways out, and we also know the amount of time that we have to burn the engines. In total is going to be 27.14. The TTHD, in this case, the TTHD is the descending node. That's going to be 27.15. So using the full power of the main engines, we need to do a burn that's going to last 27.15 seconds. So when do we do that burn? We do that burn when the time to the node is about half of that number. So half of 27 is like 13.55, something like that, would be 27.15. So when the time to the node is 13.15, we will do a burn using the full power of the main engines if we choose, or we could use partial power on the main engines because of the drift that I talked about with the autopilot. And that will bring the relative inclination down to 0. So let's go ahead and warp time forward and get close to the time to the node. Again, we don't want to go all the way there because we need to give the autopilot time to settle. So I'm just going to warp time forward until we're at about 100 seconds. A little bit farther, about right there. That's good. Now back to real time. Now we'll go orbit plus. And notice that the time to the node is still counting down. That's why we do this ahead of time, so we give ourselves time for the autopilot to settle. And now that the autopilot is basically settled, we can just kind of hang out here and wait for this to get down to about 13 seconds or so. Now again, the autopilot in the Delta Glider is tuned pretty well for holding in the orbit plus position, so we can get away with using the full power of the main engines because we're using the Delta Glider. If we were using the Raven Star, I would definitely not recommend using the full power of the main engines because the autopilot won't hold that center position well enough. Go ahead and warp time forward. Okay, again, we're going to be at about 13 seconds when this will switch from kill thrust, so let's get our fingers on the button. And here we go, full power of the main. And got the main engines locked. Now I'm just going to watch the relative inclination. And you'll notice it's having some impact on our PEA. That's okay. It's actually a good impact on our PEA at the moment. And when we get down near the bottom, we want to press Control and start backing off so we don't overshoot. Let's back off some more. And let's kill the engines, and we got lucky and just killed it right on time. If you overshoot one way or the other, switch to translation, and then use 6 or 9 to correct accordingly. Okay, now that we have our relative inclination down to 0.00, we can go ahead and turn off normal plus, and now we need to shift our focus to the next priority. And the next priority is going to be to circularize our orbit at apoapsis. And you can remember from raising and lowering the orbit, that video, that we know that when we know we're going to get to the apoapsis because the time to the apoapsis is given to us right here. That's in 750 seconds. Let's go ahead and warp time forward to get closer to that point. And we'll go out to about 150 or so. When the APT is about 150, then we'll come back to real time. And we'll press prograde to give the autopilot time to settle. Now we're only going to be raising our PEA by 140 kilometers or so, 150 kilometers. So we don't need a lot of time to do that because these engines are very, very powerful. So we can get the time to the apoapsis down all the way to just a few seconds. And notice that I'm at 10x and I still have the ProGrade Autopilot on. That's okay because we're only warping time forward by a few seconds. If you warp time forward by minutes and hours and especially days, you always want to turn off the autopilots before you do that, because these autopilots use small amounts of RCS to keep the vessel in position. And if you warp time forward a lot, you'll actually run out of fuel if you leave the autopilot on. So as we get down here toward the bottom, about right there, go ahead and full power on the main and just get this orbit circularized. And I'm just kind of watching the eccentricity at this point. And there we are. We got a 0.000 eccentricity. And our PEA and APA are just about 200. We're a little bit under, but that's okay. And somehow or another, that affected the relative inclination ever so slightly. I didn't actually see how that happened, but that's okay. If that happens, you don't really have to worry about it too much, because anytime your relative inclination is 0.005 or less, you're fine. You're going to get to the moon. The moon's a great big target. You always want your relative inclination to be 0.00 if you're going for a very small target like a space station. Those are very, very small. But the moon, you got to remember, the moon is a quarter of the size of Earth. So if your relative inclination is off by 0.01 or I should say 0.01, 0.02, something like that, it's not enough to really matter. But as we'll probably have time to do another correction here over on the descending node, and if we do, then we'll go ahead and do that correction when we get over there. Okay, on 12 minutes now, let's go ahead and start setting up the MFD for getting out to the moon. Now this is going to introduce a brand new MFD that you haven't seen before, so we'll press select, and we're going to bring up this MFD transfer. Now when transfer MFD comes up, it's pretty bland. There's not a whole lot to look at here at first. So the first thing we need to do is make sure that our reference is set to Earth, and it will be since you're in orbit around the Earth. But if for some bizarre reason it says reference Sun or reference something else, press REF and then come down to the Earth and hit enter to make sure that you're referencing the Earth. Now we want to target the moon. This is done just like targeting anything else, celestial bodies, moon. Now what we're looking at here is this little green circle here in the middle represents the Earth, and this larger ring out here is the orbit of the moon around the Earth. And this yellow or orange color here is actually pointing to where the moon is currently at in its orbit around the Earth. If we were to sit here and fast forward time, you would see this line move forward, and in 14 days it would be over here, because the moon takes about 28 days to orbit the Earth once. So in 28 days, this line would go all the way around and be back where it's at right now. And this line indicates what our position is relative to the Earth. You know, if we bring up orbit MFD, you can see our orbit around the Earth is here, and that's basically just showing also here where we're at. Now, in order to get to the moon, we have to create a plan. We have to figure out the best time to do the large ejection burn to get away from the Earth and to get out to the moon. And the way we do that is by setting up a hypothetical, a what-if type of scenario. And we enable hypothetical options in Transfer MFD by pressing HTO. It stands for, I think, Hypothetical Transfer Orbit. So we're just going to press HTO, and this turns this MFD into, it's sort of like the equivalent of maneuver mode, which if you're brand new to Orbiter, you won't know what that means, but if you're familiar with TransX, then you will know what that means. So with the hypothetical transfer orbit turned on, we can now begin inputting data into this MFD to help us figure out when we need to do the ejection burn. Because the way we get out to the moon is if you think about when we did the raising and lowering the orbit video, the way we get to the moon is simply by raising our orbit. The moon is in orbit around the Earth, so to get to the moon, we just need to raise our orbit out enough so that we are out away from the Earth far enough that we will actually be on the same distance away from the Earth as the moon. But the tricky part for doing that is that since the moon does move fairly quickly around the Earth, if we were to just raise our orbit out to where the moon is at right now, and then we fast forwarded time, what would happen is by the time we got out to that point, the moon will have moved. It won't be where it was when we did the burn. It'll be about 3 or 4 days farther ahead. So we can't really calculate that very easily in our head, so this MFD does the calculations for us. Now, what we need to do, again, to get to the moon is we need to raise our orbit, and we do that by increasing our velocity. And as far as what that means in Transfer MFD, we just press DV+, and that's just saying how much velocity do we need to add. So I'm just going to press this DV+ button and hold it. And at first, it doesn't seem like anything is happening other than you see this number going up. But here in a moment, you'll see the effect that this has on Transfer MFD. So just continue pressing it and holding it, and the magic number is going to be 3.1 something. And you'll notice, let me take it a little bit farther out. Take a sip of water while I'm doing that. You'll notice as I'm putting in DV+ here, this number's getting bigger, and this ellipse, this circle is starting to grow. And this ellipse represents our orbit around the Earth. Right now it's saying if I put in 2,609 meters per second, I'm going to leave the Earth at this point over here. I'm going to go around out to that point and then come back in toward the Earth. Obviously, that's not out to the moon. The moon's way out here, so we need to increase this ellipse so that it climbs all the way out to this point. So I'm just going to continue pressing DV+ and hold it. And as we get closer to as our DV increases, you'll notice this starts to grow very quickly. Okay, so there we have it. And you'll notice also that, let's go back a little bit. Here we have no intersection. That simply means we are not far out enough to get an intersection with the moon's orbit around the Earth. But just by adding in a little bit more DV, just a couple more clicks, now we have that line that says no intersection is gone, and we now have an intersection with the moon. It typically helps if you add in just a little bit more than that. You know, when I say a little bit more, usually say 10 clicks in addition. So let's just count it out. Here we have no intersection. We press DV+ one more time. Now we've got an intersection. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's usually a pretty good number for getting enough velocity to get out to the orbit of the moon without just having a total ballistic trajectory that'll take you straight into the center of the moon. Now we need to determine when we need to leave Earth in order to get out to the moon. Because if we were to leave right now, then our orbit out to the moon wouldn't line up. Now, it's easier to understand this just by showing it. All we need to do is press EJ minus or EJ plus. In this case, it's going to be EJ plus until this gray line is laying over top of that dashed orange line, and I'll explain what that means. Again, this is the position of the moon right now. And this dashed line, this dashed orange line, is the position where the moon will be at when we get out to that point. And this gray line represents where we would be if we were to do the burn from this hypothetical point. Okay, so for example, if we did the burn from this hypothetical point, then we would be here when we get out to the orbit of the moon, and the moon would be here, and that's not what we want. We would be, you know, hundreds of thousands of kilometers away from the moon. And if we were to go forward too far, let's say here, so if we were to do the burn at this point, then we would get out to the moon, we would leave the Earth, we would drift all the way out, and we would get out to the moon here at this point, but the moon itself would be back here. So we need to lay this gray line over top of the dashed orange line, and that gives us the correct timing. So if we do the burn, this is our current position around the Earth, and we need to go forward a little bit farther. So when we get to this position on the Earth, we're going to do the burn, and that's going to send us on a 3-day journey, roughly 3 days, out toward the moon. And then by the time we get to this point, the moon will have moved from here to here, so we will have an intersection. That's simple. That's all this MFD is doing. It's helping us create an intersection. And we don't even have to use this MFD to do it. You can actually eyeball it, quote unquote, and it's not too hard to do, but this MFD makes it more precise, and we like precision. So now that we've got that set up, let me just go ahead and turn off hypothetical transfer orbit to reset it, because I think that maybe the explanation, maybe we could go through it one or two more times just to help explain it even further. So again, let's go to target, and we'll target the moon, which is already targeted, but that's the first thing that we do. Then again, we turn on hypothetical transfer orbit, and actually it saved my information. I was hoping it would reset it. Let me see if I can just reset this MFD somehow. I'll just put in DV all the way back to 0. That'll reset it. So just bear with me. Okay, that's basically the idea. So anyway, the first step 1, press HTO. Step 2, press DV plus and hold it until you have enough delta velocity to get your orbit out to the distance of the moon. And we know when we're at that point because this ellipse will show that it's touching the yellow part or orange part, and this no intersection will go away. So just keep pressing DV plus and hold it, and it will always be when you're at about 3,100 and somewhere around this number. It won't be exactly that number because the orbit of the moon does change slightly depending on its position around the Earth, but it will always be close to this number. Whereas when you go to some of the other planets like Mars or Jupiter, the orbit around the sun is so vast that the amount of delta V required can change a lot more. Now, so step 1 was HTO, step 2 was pressing DV plus and holding it until our orbit got out to that point. Now step 3 is you press EJ minus or EJ plus until the gray line is laying straight over top of the perforated orange line. So that's what you have to do. Okay, now you still have time to actually complete the ejection burn to get out to the moon, so let's go ahead and do that. Hopefully those 2 explanations were sufficient to understand what we have to do there. So what we have to do now is warp time forward until we get over to this point. We are here in our orbit. Again, that's there, and we're going to do the burn when we're about there, or so when we're about here. Now, again, we're going to cross the descending node before we have to do the burn. So what we can do is we can actually, I think we're going to cross it. Maybe we're not. No, we're not. I lied. We are not going to cross the node, so we're not going to be able to do any additional correction. Why is this off so much? And it was off by 0.02, and it's just continually getting worse. I actually don't understand that, but I will deal with that another time. So we're going to go ahead then and just warp time forward until we're over to this point. And yeah, you'll notice my relative inclination is continually getting worse. I'm actually quite stumped as to why that's happening. It could be because my altitude is low. Well, relatively low. You know what I'm going to do? Yeah. So these sorts of things happen in Orbiter, and this is important. Some people would say at this point that they would stop recording and then they would go back and re-record and do everything so that it was perfect and everything wasn't a surprise. But I actually don't like to do that because these sort of surprises happen from time to time, and you need to know how to deal with them. So we're going to abort our moon. We're going to abort our plan for going to the moon for now, and we're going to deal with this relative inclination problem. because now our relative inclination is high. It's off enough that it's actually a little bit of a concern. We would still get to the moon, but we would have a fairly large plane mid-course correction to make. And so I'm just going to go ahead and deal with this. So I'm going to turn off hypothetical transfer orbit, and we're just going to abort the plan for going to the moon for now. And we're just going to figure out what's going on here. Why we are... Actually, I know exactly what the problem is. I recently enabled non-spherical gravity sources. I forgot that I did that. And normally I don't have that enabled. And this is one of the reasons, because the MFDs aren't accurate enough. So here's what we're going to do. We're going to come around to... Okay, here's what we're going to do. We're going to press Control S, and we're going to exit Orbiter. And we're going to turn off non-spherical gravity sources. So we're going to disable that perturbation. Somebody actually pointed out that I was mispronouncing it. I want to say permutations, because the word permutations, when you have mathematical permutations. So when I see this, I consistently think of permutation, but it's not permutation. It's like perturbed. The orbit's perturbed. Okay, so we've turned that off, and we'll go back to scenarios, and we'll go to the quick save, and it'll be this one. We'll go to launch orbiter, and now that perturbation is off, we'll see what we have. It's actually preferable if you have that particular...
Welcome aboard,
this
Commander.
is not the right scenario.
All systems
It's actually preferable if you have that I forget it. That thing turned on if you are using a certain MFD called IMFD. Okay, here we are. But if you're an absolute beginner, you want to leave that particular realism setting turned off, and this is a great example of why, because it does things that are somewhat unpredictable due to the fact that Orbiter doesn't model, like Orbit MFD doesn't model that particular realism setting. Okay, so again, we aborted the plan for going to the moon, and what we're going to do here in the last couple minutes of this particular part of the video is we're going to just fix our altitudes. We're going to bring our PEA up, and we're going to bring our alignment back with the moon. So we'll come around to the descending node. That's the first order of business. And we're almost there, so we'll come back to real time, and we'll go orbit plus. Again, it's orbit plus because orbit AN equals AN, and we're at the other one. I'm going through this part a little bit quickly so that we can just get back on track with going to the moon. And we're going to do this burn when Tn is less than 1 second. So we're going to go ahead and warp time forward to get to that point. It's going to be a very small burn. We could even use translation thrusters. In fact, let's just do that. So here at 10 seconds, we'll go ahead and just start translating. Actually, we're going to need more translation, so go ahead and use the main engines. Okay, there we have that. So let me go ahead and turn off normal plus. So so you can see this is actually a good example. I'm kind of glad this happened, because you can see that just because things don't go exactly according to plan, it doesn't mean that you have to abort the mission and start over. You can always save the mission. That's sort of something that should be understood. And now we're going to come around to the periapsis if we have time. Actually, unfortunately I skipped the periapsis. Rather, we're going to come around to the apoapsis and raise the periapsis. So let's go ahead and warp time forward to the apoapsis. We know when we're going to get to that point because of the APT value. So we're going to go all the way down to 100 seconds and then go to real time. And we don't really need to do this step, but we're going to do it anyway because we have to go around. Now we'll go to prograde, give the autopilot time to settle. And we have a very, very small burn to here. We're only going to raise the PEA by 20 kilometers, so we don't need much time to do that at all. So we're going to bring the APT all the way down to basically 0. And now we'll... I unfortunately just overshot that horribly. That's okay.
Rotation. Translation.
If I want, I can translate backwards to correct that little bit of an overshot there. You can see the ECC. And that's just one of the dangers of pressing the plus key and holding it like I did. I should have known better. You just press control and plus. That way you're not using the full power of the main engines. But this is no big deal. When you're going to the moon, you don't need a perfectly circular orbit, but it's preferable if you do things like according to plan. So we'll go ahead and correct and get our ECC back to 0. So we're just wasting a little bit of fuel. Okay, there we go. That's good enough. So we've got an APA of 208, a PEA of 206. Certainly good enough. Now we'll go ahead and end this part of the video since we're at 30 minutes, and we'll pick up here when we come back. If you like this part of the video, please hit the like button, subscribe to the channel if you like the content, check out my Facebook page where I post all my videos. I post various images and other space-related content, and I'll see you in the next part. Kilometers, and we've got our orbit basically established. It's in pretty good shape, but we still have a couple of things to take care of. The first priority when you get into orbit always is to make sure that you're going to stay in orbit, because it doesn't do a lot of good to do other orbital tasks if you only then go around the globe one time and get into the atmosphere and burn up. So we want to first just see when we need to do our orbit circularization burn. That is always the #1 priority when you get into orbit. And I can see here the time to the apoapsis is 1,473 seconds and counting down 1 second at a time. And the apoapsis is here. If I press mod to get rid of the information, you can see I'm here and my apoapsis is here. And again, that is 1,459 seconds away. So the highest priority for me is to make sure that I get to that point and circularize my orbit. But there are other things that I can do in the meantime, because I can't circularize the orbit until I get to this point. At least I can't do it efficiently. So if there are other things that I can tend to before I get to that point, then I want to tend to those things. One of those things that I can tend to is my align plane. I can see over here in align plane MFD that I'm going to reach the descending node in 663 seconds. Now, it's pretty easy to understand that 650 seconds or so is a lot less than 1,400 seconds. In other words, I'm going to get to this point and I'll still have 800 seconds until I get to that point. So if there's something that I can do at the descending node, I can go ahead and tend to that first. I don't have to. I can skip it and take care of the orbit circularization and then do the align plane. But since I'm going to come up to the descending node well ahead of schedule for getting to the apoapsis, I want to take care of this first. So I'm going to press H to change over to orbit Earth. And now that I'm in space, I can switch over to the, go back to part 1 and watch all the videos in order. Now that I've said that, let's get back into the flight here, where we're eventually going to get to the moon. Now in the last video, we took off from Cape Canaveral, and I just discussed a couple of basic concepts, such as making sure that we're going to arrive at Brighton Beach when the sun is up, and then we talked about, getting up into orbit while having our relative inclination between our orbit around the Earth and the moon as low as possible. So let's go ahead and continue. Let me unpause the video here, or unpause the simulator. Now we just did reach main engine cutoff, so we're here at 96. Okay, welcome to another Orbiter 2010 video, and this video is going to be a direct continuation of the previous video that I did in my Absolute Beginner Guide series. This is a series that I'm putting together that has a special emphasis on people who are brand new to Orbiter. You've downloaded the program, you've got it installed, but you really don't know how to do anything with it. So if you watch these videos, we'll learn how to get into orbit, we learn how to raise and lower our orbit, we learn how to do plane alignments, how to get to the International Space Station, how to land. And in this part of the series, we're learning how to go to the moon. So I'm assuming that you've already watched all of the previous videos in the series, so if you're happening on my channel for the first time in this video, then you're going to want to stop this video